Today I'll cover the topics on how to draw the Newman, Fischer, and Haworth projections starting from the bond line structure of organic molecules. So let's start with Newman projection. So what does a Newman projection do? So Newman projection will convert a 3D bond line structure to a 2D ball and stick model. It helps us to look at the strains in the molecule, like the Gaussian strain, torsional strain, and helps us to find out which conformations are more stable than others. So let's consider a simple example like butane. You can see this is butane, 1, 2, 3, 4, 4 carbon atoms. The two metal groups are on the same side. So what we'll do is we'll rotate it along this carbon bond, and you'll have something like this. So you view it from this way, and the carbon atom which you see front, you are going to draw it right here like this in the center. So this is the carbon atom which is right in front of you, whereas the carbon atom which is in the back is drawn as a circle, and the substituents attached to it are drawn attached to the big circle like a ball. So that's the reason it's called a ball and a stick model. And so this projection is called the Newman projection. It helps to see the location of the substituent on adjacent carbon. So in this case, there's a lot of steric hindrance between the two metal groups. This is called the eclipsing strain or the torsional strain. Please refer to my video on conformations to see and learn more about the different types of strains in molecules. So this atom is the front atom, whereas the big circle, is the back atom. So let's look at another example. This example is that of valine, and you always look at the molecule from one side, and whichever is the first, that will be the stick, and the carbon atom which is in the back will be in the form of a ball. So this is carbon atom 2 which is in the front, and so this is carbon atom 2, and this is represented in a stick format, whereas the carbon atom 3, which is the back carbon atom, is represented in the ball format, and the substituents attached to it are represented as shown. So this is the Newman projection of L-valine. So let's look at a few more examples of Newman projections. So I have a model made right here, and this is the carbon atom 2, and this is carbon atom 2, and this is carbon atom 3. This is bromine right here, this is the methyl group, and this is the hydrogen attached to carbon atom 2. So for carbon atom 3, this is the carbon atom 3 right here. We have the methyl group attached, we have the hydrogen attached, and this is the ethoxy group. So oxygen is here, and it's attached to the ethyl group right here. So this is the ethoxy group. So you always view the molecule this way, and look at it, and this is the carbon atom 2 that you can see first, and you can see bromine and hydrogen, and the methyl group is on the top right here, and this methyl group is also on the bottom. So these two methyl groups are opposite there. It's an anti-conformer. But if you want to learn more about the anti and other different types of conformers, please refer to my video on conformations to learn more about it. So in this case, you draw the Newman projection, you look at the carbon atom 2 and you put it as a stick format, which is shown right there, in the back atom, which is connected to the ethoxy and methyl group, is shown in the form of a ball shape. Okay, so this is carbon atom 3 right here, and this is carbon atom 2, the front carbon atom. Okay. So you can look at another example of mesotartaric acid. Here the carboxyl groups are on the they're in the anti-position, opposite directions. One going up this way, other is down. And you look at the molecule here, and this is carbon atom 3 and this is carbon atom 2. So carbon atom 3 is, you can look at the carbon atom first, and so it will be represented as a stick, whereas carbon atom 2 in this case is the back carbon atom, and so it's represented as a ball and the substituents are attached. So let's look at Fischer projection formula. So what does a Fischer projection formula? Will convert a 3D bond line structure of a chiral center into a 2D cross model, and it's useful to assign absolute configuration of the chiral center. Remember that you'll not always not have models to make out of to make models out of the molecule. And so it's useful to have a 2D structure to assign an absolute configuration about a chiral center. So in order to assign the absolute configuration, you have to make sure that the lowest priority group is on the top in a Fischer projection. Also, remember that you can rotate the Fischer projection by 180 degrees, or you can perform a double exchange, and we'll do that in an example. Let's consider the example of valine. In this case, the carboxyl group and the isopropyl group are away from the viewer if you are looking from this way, and so these will become the vertical lines in a Fischer projection, whereas the hydrogens and the amino group are towards the viewer, and so these two groups will be the horizontal lines in the Fischer projection. So this is how a Fischer projection will look like. The amino group and the hydrogen will be the horizontal line, whereas the carboxyl and isopropyl groups will be the vertical line. So let's see how to assign the absolute configuration of this chiral center. So you see, this is a chiral center because it is attached to 4 different substituents. The 4 different substituents are hydrogen, carboxyl group, amino group, and the isopropyl group. In order to learn more about how to assign the absolute configuration in the hash-wedged structure, please refer to my video on RNS and DNL absolute configurations and how to assign them. So the first thing you do, you write the Fischer projection formula, and in this particular case, the lowest priority group is hydrogen. You find out the priority of the groups. Again, if you need to learn how to assign priority to the different groups, and please refer to my video on RNS absolute configuration. So hydrogen is the lowest priority group, so according to the rules, we need to ensure that the lowest priority group is on the top, and so what we do is called a double exchange. You see this double-headed arrow, so you have to draw 2 double-headed arrows like this, and you can exchange these 2 groups. Let's call the double exchange. So here what I've done is hydrogen and carboxyl group have exchanged positions, and amino and isopropyl group have exchanged positions. Okay, and once they've exchanged positions, now the lowest priority group is on the top, and you can then look at A, and you can follow and trace the path from A to B to C. You can see from going from A to B to C, this is counterclockwise direction or path, and so the absolute configuration about this chiral center is S. So let's look at the Fischer projection of mesotartaric acid. So in this case, this is a hash-wedged bond line structure. It's called SYN because the two carboxyl groups are exactly the angle between the two carboxyl groups is 0 degrees. That is, all the substituents are aligned perfectly. You can look at in order to draw the Fischer projection structure, you'll have to make sure that the horizontal lines, in this case the hydrogen and OH, are the horizontal lines, and the carboxyl group and the carbon bond is the vertical line. So that's how you draw the Fischer projection of mesotartaric acid. Let's see how to assign the absolute configuration about carbon atom 2. Here in this molecule, you have two chiral centers, but we'll focus on carbon atom 2. So we'll use the same set of rules. We will write the carbon atom 2 like this. So we have the carboxyl group, hydrogen, OH, and this is a whole group, which is written as CHOH, COH. So it's CHOH, COOH. So the hydroxyl group and carboxyl group. Okay, so we are going to do, you can see that hydrogen is not on the top. It needs to be on the top before we can attempt to assign the absolute configuration about the chiral carbon 2. So we are going to do a double exchange, double-headed arrow. So hydrogen and carboxyl group will exchange, and OH and this big group will also exchange. It's called double exchange. So you can see that we have exchanged the hydrogen and the carboxyl group, as well as the hydroxy and the this big group. And once you have done that, then you try to trace a path from A to B to C. As you can see, going from A to B to C, this is clockwise, and so the configuration about the chiral center is R. So let's look at the Haworth projections of D-glucose. So why do we need a Haworth projection? Well, it converts the Fischer and 3D bondline structures of simple glucose to the cyclic structures, which have been observed experimentally. So D-glucose exists as a cyclic structure, not a 3D open chain or a Fischer structure. And that's the reason we need to learn how to draw the Haworth projections. It also shows a new chiral center that's formed because a ring is formed, and that's the anomeric carbon, and we'll cover that. It's also useful to see the positions of the hydroxy groups, whether they're cis or trans with respect to each other. So there's a lot of advantages in drawing the Haworth projections. So this is the Fischer projection structure of D-glucose. The aldehyde group is right on the top, and you can see that the OH group on carbon atom 4 can react with the aldehyde group and form a 5-membered ring. And this is the 5-membered ring that's formed. The term beta is used when the OH group is on the top. And this is the new carbon atom, chiral carbon center that's formed. Is called the anomeric carbon atom. And this carbon belongs to the aldehyde group right here. So if the OH group on carbon atom 5 reacted with the aldehyde group, then you'll get a 6-membered ring. And in this case, the OH group is on the bottom, and hence it's called the alpha form. Of course, you get the OH group can be on the top or bottom, and if it's on the bottom, it's called alpha. If it's on the top, it's called beta, glucopyranose. And you have 36% of the alpha, and the rest is the beta form. The 6-membered cyclic ring, these are the Haworth projections, and this hydrogen is above the 6-membered, above the ring, and this hydroxy group is below the ring. This is the anomeric carbon atom. That's the aldehyde carbon. Okay, and it's the chiral center. It forms a new chiral center. Thanks for watching. Like and subscribe.